All right, that's good. You guys see anything?
Yeah. Oh, hell no, I think that. So I might have done this. Now, and be like, hey, I don't know, I like, is that your idea? Can you do that? Or should I like apply all of them? Yes, it's the North Side. Thank you very much. And I'm going to say, and look at second. No, it's a Philippine community chat.
Okay, guys. So if I'm gonna meet with quite a few of you who had questions on this stuff Tuesday, do you guys want to talk about it right now or ask specific questions, or was anyone successful in terms of getting everything? Cool. So then there's people you can ask.
Properties for the other one, like the one where you manually input.
For the second spreadsheet?
Yeah.
So the geometries are what you're actually going to be sliding through. So it's
and then do you have to just plug in the formula for II?
Exactly. Yeah. So that's the only math you have to do.
And then what did we use where you had an A min and an A max? What did we use that spreadsheet for?
That's not part of the assignments, but the thinking there is, which you couldn't hear, is that if you're in some design process and you had a range, you just wanted to see the available options. And this is more likely helpful if you knew like ZX, like what you wanted the flexural capacity to be, but you didn't know what depth, because a W8 could do it, but a W12 could do it as well. And so you just wanted to see all those options. So that's just a sorting exercise. But you'll see the sorting exercise might be helpful in a bunch of cases. Okay, so hopefully you guys feel pretty good so far with the exercise you've done on Excel or have started. So it's just gonna open up super free from here. I'm gonna have in session or in assignment 6, I'm gonna ask you to just start what will hopefully be a long-term project personally for you, which is just making engineering easier for yourself. That's what the project should be called. And it's all the things you guys have to go through for steel design, concrete design, and all these little checks and all the homework. Hopefully you'll just put in any aspect of that felt tedious to you, just try to automate it for yourself. And that's the whole point of using Excel. I was actually just, again, a lot of what I'll show today is probably going to be a little bit rough because I'm sort of learning this on my own as well. But Professor Miranda was just showing me all these books from like the 70s of when they didn't have computers and they had to deal with design checks, or they wanted to streamline the process as opposed to going through all the actual equations. And so I'm going to, at some point, pull up an image, but they would know that there are these overall proportions or ratios between like the initial inputs and then the types of reinforcement you need, or the sort of capacity of the beams. And then what they would do is they'd print in their like AIC books these pivot tables where like you can sort of like draw what it would look like. But you would sort of have on one end in either logarithmic scale or whatever, you have like the moment you want to design for. And then over here you have another one on a completely different scale. It might not even be matching here, but then you've got, I don't know, like B, and then you've got D here, and then you've got like a thing that says pivot, and then you've got your reinforcement ratio here. And basically you would like plot this point and that point, and then you draw a line there, and that becomes your pivot point, and then given a B, that tells you your row. And so like that just seems super archaic, but that's exactly what a spreadsheet will do for you, right? And so that's the whole concept of us automating work for ourselves, because this is just streamlining all those formulas back in the day when they didn't have spreadsheets. And the other way to think about this is a lot of the parts you guys might have seen in concrete or in steel, where you've got an actual, let's say, the one we're going to try to build today together. You got rho on the x-axis. You have m, your moment capacity over, let's say, normalized to BD squared. And then you've got this chart is for a given Fy of steel, let's say 60 KSI. And then you're going to plot for different values of F prime C, let's say 3 KSI, 4 KSI, et cetera, et cetera. And you're going to plot like lines. They're not going to be exactly linear, but this is really that we're going to talk about the formula that gets you this, but hopefully you know this from concrete. But what you'll do is once you've created a table like this is plotting a bunch of individual designs. And that would take years and years to do if you were just doing it by hand. But spreadsheet will plot this for you. And then later on, you'll just say, okay, if I know what moment I'm designing for based on the uniform load on the slab or on the beam, then that's the row I need, given which line I'm looking at here, right? And so that's exactly the kind of thing that with brute force computational methods, you build yourself a design check or a little slider tool or just a line that will get you really quickly to this without any math. And so this is just one example, and we'll show this today, and hopefully it'll show you something interesting about, does this really even matter? We'll talk about that. But I want you to take away from today, when we do this graph together, that you can make a graph for anything you want, anything over anything, as long as it'll streamline your process. Because the individual points are those individual designs. You don't care about going through one by one. You just want to create the trend line, and then let this be a quick check for yourself as you're doing design. So we'll get to that. But hopefully you guys have a sense of what assignment 6 is about. I'm gonna expect a very simple spreadsheet on gravity load, and then one on one-way slab design and T-beam design. This will be a super oversimplified design where obviously this is assuming that you're gonna have a one-way slab system on a floor, and that it's gonna be a T-beam concrete, which is basically a concrete beam under concrete slabs. And then it'll make a bunch of other gross assumptions too. But what this should mean is that this is the first thing you start inputting numbers into when you're in your design phase with your architect and you first get that floor plan. Remember when we were doing the hand drawing exercise, we were like starting to build like what is that bay width, the grid width? Right in tandem with that, you should be playing on your spreadsheet, because what you decide there is it 10 feet, 15 feet, 16 feet on the one-way slab span is only dependent on the amount of load you're expecting, right? And you should be able to see that very clearly once you do the spreadsheet. So you'll know that, okay, if the load is going to be a standard load, then 10 feet on my spans makes sense. And that's the spacing between your secondary beams. So you have to sort of do that check back and forth as you're actually selecting, here are my columns and here are my beams. So that's where this fits in, okay? But then once you've done those initial checks, it's fine if those are a little conservative, but those will tell you feasibility, right? We're only concerned about feasibility in like the first schematic phase. Of course, at some point you need to really go through and do those checks, right? Like as a responsible structural engineer. And that's really not what these quick spreadsheets we're doing are going to be for. You still should write out really nice calculations. But of course, you should also do that on the computer just because it's going to look nicer, right? And so we'll talk about just formatting nice calculations. And I recommend that when you guys do 183, try to just be professional enough that you don't do many handwritten calculations. You just do it really nicely formatted on a spreadsheet. And it will just make you, certainly save paper, and it'll save you time, I think, as well. But there is a difference between these sort of iterative spreadsheets we're going to make with the tools and the lessons we learned last time and like the final calculations. You still have to do final calculations, of course, right? And that's where you have to write out all your math and whatever. So before we go into anything, I just wanted to show you a quick video. I realize I need to link audio, which hopefully works. But this is going to just be a flashback to SketchUp, hopefully. I just want you to think a little bit about SketchUp needs. Okay, so hopefully you'll just be able to hear it from my laptop. Let's watch this. I just saw this the other day, and this is pretty recent. And it's kind of a crazy building, but this is like real life, right? So this is exactly the kind of thing you might be presented with. All right, I'm just gonna have to try to hear it from my computer. Oh, geez, I don't know why it's. Okay, well, I'll be Bjarke and go then on narrate this. So this is this is an architectural practice in Denmark, which is famous for one thing, and this is what he's describing at this point. But they do architecture which looks strange because it responds to their environmental conditions. And with for example, this one, which will be in New York City, it's all about having really nice views on like a constricted sort of airspace on the plot. And then he talks about this crazy tower here, which makes no sense, and then this guy right here, and then he goes to like, okay, now we're going to show you the Vancouver project. And by the way, BIG has awesome graphics here where they like interlay CGI directly into the videos. But he talks about this plot right when you enter Vancouver on this what will become like a Canadian High Line, and then he sort of shows, there's this plot of land which is right around this fork here, and it's a triangular plot on the ground. And it's really restricted because you have to be 30 feet away from the bridge, and then they have this specific setback that they need for like a park. So it's this guy right here. So that's like a triangular extrusion straight from the ground, easy to do on SketchUp. But then he's going to like show his main innovation in a few seconds. So this is another setback they have to respect. So these are all the things that the architects care about, right? They care about these, like where can they build massing wise. And he goes, okay, well, the 30-foot requirement is to the bridge, so we can actually rotate that on a pivot and say that actually once you get a certain height up, that doesn't matter anymore. And then his architectural revelation is, oh, then the building can do that, right? And so everyone in this room is like, oh, fuck, right? So then he's going to propose this right away. The curious thing is that he talks about all these great things that this one architectural move does. It's basically a rectangle on the top, a triangle on the bottom. And not once in this video does he talk about the structural needs of that. He just gives, that's the given, like given that this will work, like these are all the amazing things you can do. You have more floor space, you have premium, rental at the highest floors at the premium views. You get this incredible look. So that's the language of architects, right? They assume that we're going to do our job. So like our first check is that, oh, can we actually do our job, right? Right, of course, yeah. But at what cost, right? And so like that needs to be communicated because clearly they're not going to get those numbers. They're going to jump right ahead to the next part of the conversation. And we need to be right there for that feasibility check and hopefully be really supportive and strengthen their ideas. Anyway, so I just wanted to show you that. By the way, when you guys see this tower, do you immediately have an idea of how you would model that in SketchUp? Thoughts? Maybe try it on your own. I won't make it a deal, but you should very easily be able to do this based on what you've learned. The one hard thing might just be that S-curve, but just think about like if you were to take this design, which very much could be what the architect gives you, because you might have a triangle side, right? But just think through the exercises we did. You build the shell, or it's given to you, but then you built the mass floors, and you start to do a wireframe diagram. You pick out the lateral system. All those things should start running through your head right away. That's just the reason we've been practicing this quarter. Okay. Yeah, he is really cool. And then the other one I was going to show is the building that looks like a Chinese character. It's like an Eiffel Tower. You should start to look at these things online as like the sort of innovative architecture and think just, what is the number one most critical structural thing I need to design in that building? That's just a good mental exercise to start to go through. So I want to spend a little bit of time.
That building, would it just be like really where it curves, just really heavy lateral like bracing, so that it would be able to go into the center of the building and go straight down? That'd be like the most important part.
I mean, I don't have the right answer. I feel like what you would do is the diagonal would really be the strong lateral system because that's constant all the way up, and you just have to deal with the cantilever individually on each floor from that point. But you would pick that longest one just to give yourself some feet. So I could spend hours and hours talking about this project. I won't that much just because we're short on time. But this is a website you can go onto that Stanford was nice enough to make. But this is the house we built as part of the Solar Decathlon project.
different from the Solar Decathlon website?
Yeah, this was reporting done by Stanford News. So there's a lot of really cool videos actually in here that are much better than what you would find on the Solar Decathlon website. But I'll just say, just based on my experience, that the schematic design took over a year, and it was basically this process in which, if you think about the number of architectural models there were, at some point there was like 4 options, and then there became 12 options, and then it became 3, and then it was back to 8, and it was just this like back and forth. And just think about how tedious that must have been from a structural engineering perspective of having to deal with all those iterations. And there were really serious concerns through that whole process. It wasn't like we were just like, oh, let's now have 8 concepts. That we were really breaking through on serious concepts and serious constraints, and just it takes a long time to realize them because they're so interdisciplinary. But just know that as an engineer in that process, the one thing that makes you better is your speed at which you can get information back to sort of react or respond to new designs. So when I was doing this project, I really just took the structural engineering for granted. It wasn't my job, of course. We just like pitched it to the structural engineering department and said like, hey, we need some second years to really step up and do this for us. It'll be a great learning experience. The people who are involved are, I think, all at Arup now working. But
Holmes Poly?
Yeah. So in preparation for this class, I just sort of realized like, hey, I've never actually, like, we had this like 10 gigabyte Dropbox with, as you can imagine, so much stuff. And I never ever really looked at the structural engineering folder. I was just assuming that they would, like we would build a 15-foot door. Like, yeah, of course they'll be able to structural engineer. And it turns out that was really hard, but we didn't care so much about that because we just treated it as a given. Or that we would have this sort of incredible clerestory, which would be like the main feature of the house to get natural light in. Like that required steel and like a full-on shop drawing, something, a Virendale truss that was brought in on a 50-foot truck. Like only in hindsight do I realize like maybe we could have talked a little bit more about that decision cost-wise. I still think it was a good decision, but like that really was a critical part of engineering. So what I did recently is I just sort of brought back the structural folder, and I thought we would just spend about 10 to 15 minutes just exploring this together, and I'll go right to some of the critical things, which I've also put on the Dropbox for you guys, and of course they gave me the okay for that. They also gave some really nice feedback to some questions I had. I'll just let you guys read these. They're really, really good. And I asked them really targeted questions about what it was like to deal with designers like me. But in this folder, I'll just go to one really quick thing so far. There were these milestones in design, 80%, 100%. 100% is where like this has to be stamped by an engineer and ready to go for construction. 80% was like close. And you can just see this as analogous to like week 7 versus week 9 of next quarter. But in their final submittals, I first wanted you to note that they have a lot of SketchUp models in here. They actually always had their own SketchUp model. And often this was just copied directly from the architectural design, but they were doing the exact same thing I've been showing you guys. Like given a basic architectural model, start to build just the structural parts of it. And that was really helpful for them. They also happened to, let's see, where did I find? Like if we just open, they obviously had to learn a lot of timber design, which you guys won't have to deal with, but they grabbed a lot of their loads and codes, not from what you're used to, but from companies. They had shop drawings they had to do where this was that Virendale truss I was telling you about, where they had to specify obviously the dimensions and what these different members were, the type of welding that they were to do in the shop, and just little details like this. But this is after, of course, you've completely calculated what this will be. So let me go into the 100% calcs. Oh, one more quick thing. At some point, we were going to put the entire house on base isolators, which would have been this amazing architectural or engineering innovation. Like they wanted that one thing that was awesome about the house from a structural point of view, and we ended up taking that out because of cost. But that was their moment to shine in terms of creating an engineering innovation. And I highly recommend you guys put forth something like that for your project, because you guys don't have to care so much about cost. But it's a great experience to start to weigh trade-offs between something that's really cool architecturally versus something that's really cool engineering-wise. I mean, for base isolation, you never see it in action until you have an earthquake, right? So it was a hard sell, but yeah, that was an interesting piece. And they spent hours and hours, and then we just decided no one day. That sucks, but so they did. So a couple things I'll show here. They have their drawings. We'll look through them just briefly. They have a lot of these guys, so this should look familiar as SketchUp. And what they're really doing here is they're looking at specific parts of the house, and they're just grabbing a screenshot and putting it directly into their calculations, because it just is a nice figure of reference of like what you're currently calculating. So here they're talking about shear walls mainly, and this is just help. It was a nice link between what they could grab from the architectural folder and what they could work with. They also had hand drawings. So again, this is like something that's not to be forgotten. I have a feeling like, well, some of these are just real specific details. Like this was an overhang, which you would only have to deal with this detail because this couldn't fit on the highway, so we had to like take off the overhang. So of course, like this wouldn't matter on fixed ground construction, but this was like a really hard structural detail. And then they wanted to really show what that would look like to us to build, so they did a nice hand drawing there. This one looks like stuff like that. So there were a couple of hand drawings they had in the final submittal. They also had hand calculations, but I suspect that was just because they ran out of time. And it was a sort of a last minute kind of thing. But just this is a proof that hand drawings are still really critical. So let's look at some of the drawings. You always have this first page of general notes, so you guys won't have to care about that for now. But I just want you to take a look as I go really quickly as what's the overall level of detail and what's the organization. You start with foundation, and then sort of you go up from there, just in the framing of your floors. And this would be the gravity load systems we're talking about. Then you switch to elevations, in which you're just still showing overall geometries, sections. A lot of these are really, this is almost like the first part of a drawing booklet is often like a table of contents, where this will take you to a more detailed drawing somewhere else. But this just lets the viewer get an overall perspective on things. And then we have to deal with like ADA ramps and stuff like that. But then you get into these really tough details. And you guys probably won't get to this stage for most of your tower, but I think the architects will go through a pretty detailed wall section exercise. I think it will be really a good experience for you to be part of that experience of like, you want to make sure that the structure they draw is really the structure as it is in full dimensions, and then you'll gain an understanding of how the structure relates to the finishes around it. And if you feel comfortable in SketchUp, you could draw all of that in SketchUp too, to have exact dimensions. So yeah, we go through all of that. Now I want to bring up the calculations, which is what we're really going to focus on today. I think it's going to be here. So this is the calculations. First of all, notice it's 188 pages. And also notice the stamp. So this is the licensed structural engineer we work with, Dagan Kobe out of Oakland. And the one guy there was a Stanford alum, but he was first and foremost a mentor through the process. But the structural engineers at Stanford did everything, and then he just put his stamp on it once he reviewed it. And so this really was designed by Stanford students. The table of contents, let's quickly look at. It should look very similar to what you would expect. Start with the gravity. This is just particular to the type of structural system we were using. And then you go to the lateral loads. That should be very ingrained in your minds at this point. And then you go into a little bit more specific kind of things. Like in our case, it was that steel piece. There was shear walls that we had to deal with as the one main lateral system. Diaphragm, I don't think you guys will get to, but if the wall breaks off of the floor, that's a big problem. Foundation design, and then a bunch of other things. This was that 15-foot span of a sliding door that they had to dedicate a whole chapter to because it was a special design. And then you have a bunch of stuff in the appendix, which you'll start to recognize some structural analysis there. Let's just take a look at what this is. So gravity takeoff. This is roughly what I'm expecting you guys would use in 183. It wouldn't really get down to the detail of individual parts, but at least you'll have types of dead loads, types of life loads, and then you'll have your PSFs here. And then obviously you'll sum it up here. So this is what I mean by that first spreadsheet. It's a simple table like this. But these numbers become critical for the rest of the project. The reason they're showing 3 different columns here is just because when you design the floor, it doesn't care about its own self-weight as much as the next part and down. So this is going down the load path to get more and more weight. So they were just doing that all at one point. And you could maybe consider doing that in your gravity load spreadsheet, because we're going to be designing by load path. So you start with the slab, and then once you design the slab, its weight goes right back into the gravity load takeoff, and it gives you a new WU or W for the secondary beam, for the girder, for the columns, right? So those all sort of add back up together as you go down the load path. That's what these columns mean. And then they go into the SIP design. What this is a quick table by the company that supplies the specific type of structural wall. But this is the equivalent of your steel tables, right? But just for the specific structural system. And so they actually put it into their calcs, the part that's relevant. They put a red square around what the relevant value is, and they go on with their design. And this is really good formatting that you can do in your calculations as well. Obviously, they do things like put a box around their final choice. There's always checks involved. You're always doing these checks. You always have a little if statement and then an OK or not good, OK NG is a good way to go about it. And you get into the lateral analysis. And the first thing they do is they show you a floor plan. So you grab this from your architect. You put it directly into your calculations because it just gives you a reference point of the dimensions you're dealing with. And you guys can do way better drawings than this because you don't have to put these dimensions in Excel or PowerPoint. You can put it directly into SketchUp since you guys know how to do it. So you can make your graphics look really nice too. You state the code when stuff you're going to deal with. This, remember I said in last time, is going to be that communal spreadsheet in class, so you'll have those variables right away. A lot of this just falls right in place. This is a diagram which they carefully show in each direction load case, right? So you might do this for each load combination or just in each direction, but it would really be helpful to actually show this graphically. Like, it helps you prevent mistakes, but it also clearly communicates that in this case we're talking about inverse pressure or stuff like that, right? So you set up your condition, and then you go through all your calcs, and this would all be quite automated, right? And then you bold at the end what you do. So to get a feel for just what this approach is, then they deal with seismic loads. Again, they're recalling these gravity loads from before, which you would link in your spreadsheet, and then you go on and on. They would put directly in here the site analysis, the USGS analysis. You could do that as well. And then this gets into stuff that you probably haven't learned yet, so don't worry about that. Here they show clearly where the lateral system is, and we went through an exercise like this in the drawings. But when you guys maybe do a hand drawing of this, that would be a nice thing to put in the calculations. And you've clearly indicated where your moment frames are, where your core bracing is, where your concrete shear walls are. And that's nice to just put that figure in there, because from there on, then you're just checking each of those, right? You're checking in each direction, what's your capacity. This is that design of the Virendale truss. Go on and on, so I won't obviously go through all of this. But just get a feel for how professional this looks. And when I asked them about a week ago, like, how does this compare? Like, they said, this, the quality of what they presented here is better than most of the stuff they do in their real jobs. So like, this really is like, like if you can get to this quality, you're going to be employable. Because it's so clear, right? Like anybody can review this in your firm. And then notice again, they're putting those drawings in there, and it's a really nice intersection of the architectural design and what you do. So pass forward through here, you can now start to see some bending moment diagrams, things like that. So all those things are things you can consider putting in. And then we get to the appendix, I think close to here, and you start to see some of these you can grab directly from Mastan and just screenshot them in or save them. So those are all techniques at your disposal. And then you get to the connections. And again, like I said, the connections is probably where you could use hand drawing. So they do that here a little bit. Notice how they just intersperse or combined spreadsheet printouts and scans. And in the appendix, then they really show like the full printout of forces from Mastan or whatever program they were using here. And they show all the load cases that they dealt with. And it's just really nicely laid out here. This kind of thing. You can print this out in Mastan, of course, by doing an isometric view and then just show the bending moment diagram. Okay. So that's all 188 pages. Obviously, they had much more time than just one quarter. But this should hopefully be an inspiration of like definitely achievable while you're at Stanford. And for the scale of what you're doing in 183, it won't be this long, but it could be this quality. Right? So what I did in the coursework, I just grabbed the template they were using, which I don't even know how they really set up all these parts, but this is what they were using as a printout. So this is a spreadsheet, and you can go in and do your calculations. On each one, you can clearly state what you're calculating in that page, and you definitely want to say by who, because then when you're working in pairs of structural engineers, when someone did something wrong, you can blame the other person, right, because their name was on that page. But then you just, if you had more pages, so hopefully this is a template that is pretty helpful for you guys. Feel free to use this for the rest of this class and then for 183 as well. But what we're going to do for assignment 6, I don't think you necessarily have to do it on an 8.5 by 11 sheet like this, because it's not the final calcs, like I was saying. So just this is here for you to have in the future, or if you want to start doing your problem sets in 182 on this, that might be cool. But what we'll really probably still be doing is just a large sheet like this, where we're being a little bit more hacky. Okay, so that was a very, very brief foray into the solar decathlon project, and just definitely read these comments from the engineers. But I wanted you to just notice the organization, the way they organize their work, and then the methodology using the spreadsheets, and then the way they incorporated drawings of their own or from the architect. Okay, so notes on Excel. So what we noticed last time was by inputting all the different tables you have to deal with in steel design and concrete design, you're really just saving yourself the danger of making mistakes, like literally just looking up cells. And when you're tired or when you're doing a billion at a time, like you don't want that to be the bug in your code, right? That you're trying to figure out what you did wrong. So creating something like this, as you guys have seen, hopefully just takes care of all that problem. Like this is almost impossible to make a mistake on here, unless you made a mistake in your code, then every single output would be wrong. But so that should be clear as the benefit of doing this. And you do this ideally for every table you have ever. So I would encourage you guys. I just copied and pasted a bunch of stuff from Lepic's notes. I don't know if it's the same as when I took it, but like this table is obviously critical. This is like 2 minutes to put in, right? And then you'll never make a mistake or even have to look this up again. Just have this as a spreadsheet, right? This one's a little bit longer, but I suspect this one's kind of tedious to use. But imagine if you did automate this and how easy that would suddenly be. You just give it a B and an AS, and it just tells you the next one up that works, right? It just is doing it's finding the minimum of a list. And so just think about how you would structure the spreadsheet given what we did in steel. And if you set that up for yourself, it could be quite useful even before the end of this quarter. Software for this?
Yeah.
I'm sure every structural engineering firm has their own personal built ones. And it'd be nice for you guys to just build your own right now. Now, I'm not going to require that you guys automate this for assignment 6. What you would do instead is you would have an intermediate stop point in your sort of automated design where it turns out it's recommended AS, but of course you round up to the actual AS you can do with rebar combinations. So that would be a midpoint in which the work stops. It's then asking you for an input of the real rebar dimensions and then the spacing you want. And you would, at that point, see that number and then look into the spreadsheet and then make your choice, and then it would continue from there. And so that's you're just automating everything but that part. So that's the data lookup aspect. Speed, as I said, is key just because you're in that hand drawing phase, right? You're like deciding what your grid spacing is going to be. You don't want that process to take 10 hours because you have to calculate each option. You want to iterate quickly on trace and then just change your numbers really quickly here, and it should work at almost the same pace. That's the point of speed here. And then I started to talk a little bit about an intuitive understanding of structural behavior when you have big data. And this should actually help you learn more about concrete design. And hopefully we'll see this today if we can get to it. So honestly, you guys are probably even better at concrete design at this point than me, just because it's more fresh in your minds. But let's just talk through, like, let's say we're going to build the one-way slab design and the T-beam design spreadsheets. Does that seem like a daunting exercise at first? Like, hopefully, if you get this problem in concrete, like, it's pretty easy by now, right? Like, what are the major things we talk about in concrete design? Let's assume just tension reinforcement. And let's first look at an exercise of just a rectangular beam. So we're talking about tension of steel, compression of concrete, right? And all this really is a moment capacity where this is the couple arm, right? You guys have figured out, obviously, that where this comes from is an approximation with the Whitney stress block. That comes from the stress diagram at some point looking like this, and it's crazy, so you just approximate it as that, where the amount of this is 0.85, right, of F prime C. And then this is A, which is something less than C, right, by the factor of beta 1. So all those formulas should be really easy to grab. And then your actual formula that you deal with is going to be, you're going to set, first of all, Ts equal to Cc, right? So you're going to do Ts equals Cc. You know, this is As Fy. You know, this is that Whitney stress block, right? So it's going to be the area BD, and then the Fy equivalent there is going to be that 0.85 F prime C. And I'm guessing, what am I missing here? AB, sorry. I'm missing those. So I think most of what you guys have been using is you'll take A to one side and you'll divide the rest over. And this is where you do like your A calc, right? So it's AS Fy over the rest. But then you take that A value, and then I think what you guys have been doing is figuring out what C is at that point, right? And then beta 1 is dependent on a couple of things with F prime C. And then you check if it's tension controlled, right? You guys have been doing that most of the time. And then tension controlled or transition or compression just changes your phi factor. That's the only reason you're doing that, right? So then you get all the way to the end of that, and then you have Mn, my capacity. You already know Mu, right? That was just the loads of the structure, what it has to deal with. Your Mn is your phi times any one of these, but usually you put ASFY here. And then you're doing the lever arm, which is going to be your depth all the way to the top there, minus whatever A was divided by 2, right? So you guys are using that quite a bit, right? Have you guys tried to put this into this to get rid of A? Have you done that? So it's what that looks like. So move up. So then this is going to be equal to phi AS Fy D minus, and then you put A in there, so it's AS Fy over 0.85 F prime C D over 2. Okay. And then what can you replace AS with? Where did you get AS to begin with? This sort of, sometimes you do this in reverse if you're doing analysis versus design. But AS is really related to the reinforcement ratio, right? And either you're setting a minimum or you're given one and you're checking if it's greater than the minimum or not. But what AS really is rho times VD, right? You guys have seen this? So you can input this as well, replace AS there, and then you get to an equation, actually, put it down. But I'm getting at you guys recall like a BD squared equation? You guys use that in any problems?
Yeah, BD squared.
Like the 1 minus the root of 1 minus.
Well, if you just keep on doing the algebra there, if you get to a point where you get Mn equals 0.9 rho BD squared Fy 1 minus rho Fy over 1.7 F prime C. And you get to that point, right? And that's just algebra. But like, what do you know at this point, right? You obviously know this already, or you're just working with a couple options there. You know this, 60 KSI usually. You know that, and then really your only variables are B, D, rho, and Mn, right? And then so what you've done, hopefully, is you put BD squared on this side, and then you put everything else on the other side. Usually you can, given a rho, you can actually get a real number for this. And so let's say it's just 6,000 for a given problem because you know the capacity you want to design for, which would be Mu, and then you know rho, let's say we estimated it as 0.018 prime C or Fy, something like that, right? This is like a nice assumption to go with that hopefully Lepic has shown. So you get a number here, And then all you have to do is iterate on this. Right? That's your only design problem, is just find a good aspect ratio here. And even that you probably can just guess, because you can all usually just say that B is probably going to be half of D. And D is usually going to have a 3-inch cover below the rebar, so D is just going to be, or H is going to be D plus 3. So you can actually sort of build that into here, and then here you can make a quadratic equation. And basically, you can then create a spreadsheet where you're just iterating over every possible combination of B, D, and H. And those are all possible designs, right? You can make a million of them for any given problem, but some of them are going to make no sense. You know, some beams are going to look like this, some beams are going to look like this. And often what you're constrained by is this, but in 183. The architect wants 10-foot ceiling height, right? And so you say, okay, well then if we're talking about a 12-foot floor to floor, then I only got 2 feet to work with. And that's the constraint on this. And you have like a T-beam, and then you have floor on the top, ceiling on the bottom, or space for ducting even, and you're constrained by this condition, right? So you usually know D, or you know a maximum for D. So all you really need is B, right? So if you set up this kind of thing in a spreadsheet, and it just turns out a bunch of numbers once you put in these inputs, and then your judgment is quite streamlined. You're just really looking at a nice looking beam. So let's do a quick example of that. So what I want you guys to try to build really quickly, just as an exercise, is to build that chart I was showing before. It should really just be an application of that formula. Maybe I should just leave that. Rho 0.9. Let's just assume 0.9 here. Well, let's say you have that formula and you want to use it in your spreadsheet. So just open a new Excel file. And then I want you to plot this kind of graph. So up here on the y-axis, well, on the x-axis will be phi. So you definitely want to set up phi inputs from 0 to at least 3%. Right? So like part of your Excel table will be 0.01, 0.002 as rho, all the way down to 0.03. Right? So those will be your x inputs here. In your y direction, you're going to put m, whatever m you're getting out of this, over normalized to BD squared, so that you're getting like a normalized plot no matter what your geometry is. Okay, so that will be your next values on your spreadsheet, BD squared, and then you're using the formula here, right? You sort of set it up so this goes over this side. So then f prime y, just set that up to be 60 KSI. So our graph is only going to deal with 60 KSI. So that's the comment here. And f prime c, just have a different couple of options for that. So give a value of MNBD when f prime c equals, start with 3 KSI, and then just do 4 KSI, 5 KSI, all the way to like 10 KSI. So your table that you build before you do your scatter plot has rows on the side from 0 to 0.03. And here you just have columns for 3, 4, 5 to 10 KSI as your f prime c options. And the individual cells are just computing this formula. All right, so try to do that as quick as you can. If you can't read this, just find it in your notes or just derive it again. But all you're doing is you're designing the beam, right? Or you're showing all possible options of beams. And then I'll start to do it on my screen as well, and then we'll sort of reconvene. And hopefully this takes like 5 minutes, right? These okay. Formula is going to be
screw up there. B6. It's just not know what F is.
Oh. How are you guys doing? Hopefully you got something looking like this. I've only shown one of them, but even I barely know how to use Excel, but you could show each trend line. You could show it as okay, so let me add just one more so I can illustrate something here. What the hell? Okay. Okay. So I think this is what it ultimately looks like here, if I didn't screw up again. Does anyone have it to the stage, or at least for one of the lines? So I think what this shows is that series 1 for me is my 3 KSI, and it's the lowest. It curves the most. And technically these should break off at some point, I believe, when it actually just breaks. And that's different for each. But this is just assuming you can reach 0.03 reinforcement ratio without the concrete breaking. But the last thing, let me actually put this back into scatter mode. let's just say you had a bunch of things there. I'll just make a trend line for one thing here. Equation on chart. Okay, so I just showed a trend line for just for series 1. So this would just be the 3 KSI point. But hopefully, if you guys notice, I could have made a trend line just by figuring out how to do it on Excel. But I could make a trend line for all data points, right? And it wouldn't be too different. What does that tell you? It doesn't really matter what your F prime C is, right? These are so darn close to each other that for a given 0.8, like let's say your moment was your moment normalized value was this, came over here, like it would barely be changing your reinforcement ratio. Maybe even to the point that when you got that value and then you picked the real rebar choice, like it would round up enough that it really wouldn't matter whether you had 3 versus 4 KSI. Hopefully that's just a learning point, right? And when you're talking about structural behavior of concrete, F prime C is one of the least important things compared to your depth or your B, your width, right? Those kinds of things. So hopefully that's just something that becomes obvious when you use big data. And what that really means is that whether it's a linear trend line of just 3 KSI or for all points, this is now your design equation, right? Not for the real thing, but for that first feasibility check. Because what this is a linear function, which is very easy to plot in Excel, but you just throw in your values of BD squared, which are sort of maybe architectural constraints, and then you put in an MN, and then it immediately tells you the row, and you can get a sense of like, oh, does this make sense as a design or not, right? So you can build these any way you want and for whatever purpose you want, but just see the value of you iterate on every single possible combination of a variable, you get the scatter plot, you create a trend line, and that becomes an easy shortcut for you. Okay. So what I want to do is, okay, let's say so it's 803 right now. I just want to, yeah.
Sorry, so in the values in that table, are they just MN over BD squared?
Mm-hmm. Just this with BD squared on the side.
Yeah, I'm just getting different numbers.
Oh, I might have screwed up too. So. Anyone want to contest that or agree? This is good. Okay. Okay. I screwed up a little bit here with the dollar signs at the start, but just make sure that every formula is going back to here and to here with your F prime C and row values. And then make sure it's 1.7 here, 0.9. So why don't I just let you guys, because I really don't have much more. I'd rather you guys give a shot and think through the problem a little bit of assignment 6. The last thing I'll say is be very clear about how you're designing this. So you get your gravity load, your WU requirement just from the architecture, and it's either pretty standard or they're telling you that this is a tower with trees, right? So we've got like a green roof skyscraper. Every single balcony has trees on it. Obviously, that's changing your dead load, right? And you can almost consider that a live load, depending on winter or spring, whatever. But like that would be the only condition in which you have like significantly different gravity needs, right? If they decide to put elephants or trees or whatever. So the first spreadsheet should be quite simple. You need to find a dead load and a live load, and most of the time you're going to be making assumptions here, unless you can get much more detail about what they're building on each floor, right? But you have those standard kinds of things for partition walls, for equipment, for the occupancy will tell you the live load of people, right? So that's your gravity load spreadsheet. It should be pretty straightforward. You can just put dummy numbers in there for the purpose of this assignment, or you can try to figure out what the standard ones are. But you got your gravity load sheet. It's your first module, which just sort of exists on its own. You feed into it all your dead load and live load things. The factors you consider here would probably for now just be this one. But just know that when you get to, if you build spreadsheets for lateral designs at any point, you would obviously consider additional ones. So you consider it, and then out comes really this. which let's say is in PSF. Pounds per square foot on a given floor plate. Okay? So that's all you really get for now out of this gravity with float spreadsheet. You go to your next one, and we have one-way slab design. Now, of course, what I'm assuming here is that you're going to be designing one-way slabs. And if you recall from the hand drawing exercise, you set up your column grid. You have girders framing directly into the columns, and then you have these spaces. And your major question you're trying to ask yourself is, given this value, how many secondary beams do I need? Right? Because it could be just one. And then what is your span? Each one-way slab is really dealing with this condition here. Like you're designing a 1 foot by, this is 1 foot by, that was L. It could also be LN, right? It's a clear span effective length. But the L is the big question you have here design-wise. You take that L, you're then designing a slab, which is 1 foot long, and then you're putting a certain amount of rebar per foot, right? Have you guys done a design like this? This is a very easy way to think about slabs. And then you just have these all next to each other, right? So that's really what you're designing in the first spreadsheet. It should just be like a rectangular beam. This is your L. And what you'll realize is that basically L is a function of this. And so you can almost prepare yourself of what to expect. If you find this number, you already sort of have seen values. You can even set up a full big data spreadsheet of all the possible L's you'll need for different W's. Right? You can do that pretty easily if you're just constraining D. You know what D is. Right? You can do all these things. You can just, I want to leave this free for you of like, what do you feel is truly helpful for your understanding and for your speed and accuracy. But at the end of the day, you want this to turn out or let you judge pretty quickly, what the shape of this is and how much AS you need right there. Okay, so that comes from the exact thing we just did. Okay. So that's one-way slab. You got this input. You churn out your AS for slab. And then probably you want to get your D or you set it to begin with. It doesn't really matter to you. Then you go to the next one, and this is where we'll stop in terms of requirements for the class. But I'm just going to say just design a T-beam. Why? Because that's going to be almost the simplest structure you can imagine at this point. The secondary beam you've placed, which you've decided how many. It's either 1 or 2 or 3, and that's probably your only options. And you want to obviously be conservative. So make the span as much as it can be without collapsing. Right? Then you're designing this, which is a T-beam. Because you've just designed the slab, which you're going to decide what the effective length is. There are like 3 checks you have to make on when you find the minimum. You can certainly make that automatic, right? So that's, you design, you figure out your B, which you'll be designing for. And then you're still pretty much just designing it like a rectangular beam. Of course, you want to check 2 possible conditions, right? Either the A is within the flange or it's not. I'm going to guess it's almost always going to be within in this case because you've been super conservative with most things. But feel free to just assume that it's within the flange for assignment 6 or build in the check for yourself. Like you first check if A is less than this, then do this. If it's greater than TF, then do obviously a harder geometry calculation for the Whitney stress block. Just if you want, you could just assume it's almost always going to be up there, right? And that's it. So everything you put in here can literally be Control C, Control V here, right? Almost entirely. You just change a couple of your variables, but the real work is you're designing the same kind of beam. Right? Of course, this is one of a billion options, right? You could have a concrete slab on steel beams. You can have a concrete metal deck on steel beams. You can have shear studs on that. So of course, there's like a billion options. We're just showing one conservative design just so you get a design out, and then you can think about that as a baseline. Because it's nice to have a baseline because then you can do more specific designs of other options. But that's all assignment 6 is going to be. Of course, what you can do from here is do a girder design. And the one difference, by the way, when the other input, WE goes into what? WU L squared over something, right, as your moment demand. I think there's a spreadsheet in your notes where it's just giving you recommended ones. But of course, when you're talking about a beam simply supported with the moment demand or with a uniform length, the maximum moment you'll experience is WL squared over 8. Have you guys seen this formula before? You'll do something less than that because this will go down a little bit, and then you'll have negative moment and positive moment to design for. So the table you see from AIC in your lecture notes from 182 just gives you conservative estimates based on whether you're designing a span inside or on the edge or a cantilever. If you want to be super conservative, just use this value. It's always going to be less than that. Right? If you're talking about a condition here where you're putting uniform load on a beam or on a slab. So I don't care if you use WL squared over 8 or you're going to use WL squared 12, I think, for your negative moment, max negative moment, stuff like that. And that's just what this value is. Well, I don't really care. And don't feel like you have to design for positive or negative bending here. Just assume positive for now. So you can put in WL squared over 8 here if you want. Same here. But down here, you don't use this, of course, right? Because your loading condition is now a point load, right? Which is now here is like that, and moments like that. And there's a different max moment you'd expect here. Also keep in mind that concrete, one big difference between concrete and steel, when you design a steel girder, you find the maximum moment anywhere in the section, and you design the whole section to that maximum because you just have a shape, right? Whereas with concrete, you can change the flexural capacity of the section all throughout it by changing your rebar spacing. So it's actually a more economical design, but you just got to do more checks. Don't worry about that for now, but just know that, of course, that's something you have to do in concrete design. You change the rebar from top to bottom as you go over the supports and things like that. But just in your mind, like concrete has that advantage over steel because you can be very economical with where your rebar is acting. But for now, just assume you're always designing this simple condition. Okay. So if you were to continue on to girder, then you would just change your moment, your MU, to a different formula, but you're still grabbing W sort of from all the gravity loads down, right? And that was that first spreadsheet. Okay. So this is, you don't have to do this for now, but just know it'll be very easy to get to this point, and then you get to your columns, and then you go down the building, right? So that's, you can literally have a whole building automated with one click or with one WU, which hopefully feels really powerful because then you can do so much of personal checking and investigation. But this is making so many assumptions. So what you do is you have this spreadsheet at the end of this quarter, and you're always adding to it. Hopefully you never have to change anything you have because it's all correct. You're just adding more checks, adding more types of potential sections. You have a whole parallel spreadsheet for steel, which will be actually, I think, easier than the concrete one. And then you just have it on your Dropbox for the rest of your life. Does that make sense? Hopefully this is helpful. If you have any questions about this, I haven't actually made this, so I don't have like a version that will be accurate. I'm actually just curious to see, I suspect each of you will have a slightly different number of checks you're doing. As long as you like put effort into this assignment, that'll be enough for me. But I am really curious to see the way you guys think and how much you think is helpful for you. And do a check of like, if you want to run real numbers through it, then just put a homework problem in, see what happens. I'm pretty sure, I don't know what you guys do for homework these days, but yeah. Okay. So the note here is just, oh, there was a material cost takeoff. Yeah, just add one more spreadsheet. This is super easy, but just calculate the amount of concrete for a given floor. And then another variable could be number of floors, right? But then it's not useful information until you have all the pieces, but this will get at that material costs, which we will have to do in 183, right? But you should certainly automate that so it doesn't waste your time. So obviously what you do is it would be this area on a slab times the length times the width of the entire floor plate. And then the T-beam, you would just take this part and then however much length of secondary beam you expect. And just go through that exercise so you know how to do that later on. Just basic estimating. Okay. All right, so it's 8:15. Is anyone gonna start working on it, or are people just gonna take off? No, it's been a long day, but if you want to keep working on it, I'll just hang out here. If you just want to think through or at least set up your spreadsheets, in basic sense. Yeah. Has everyone filled out the survey? Yeah, most everyone. Do that quickly. Cool.
I had a question about the drawing assignment.
Sure.
So I chose the structure in Mexico,
So choosing really hard.
and it's super cool because it's entirely reinforced concrete except for like I think like right at the bases there's like V-shaped like steel wedges to support it. So I was wondering what my like sort of grid drawing should focus on to show like the like reinforcement, the structural elements.
I mean, honestly, you picked the structure in which I can't really do this assignment.
Yeah. Okay.
Which I don't really care about.
Remember I automated.
Yeah, I mean, in this case, you don't have a floor you're talking about, right? So if you could somehow show, I mean, what you would probably do as a designer in this case is you try to figure out the actual rib structure within this.
Mhm.
I'm guessing that like a critical image I'd want to see is a geometry without the arch section. So just be connecting this point to the center on all sides, and you should see like a TP, right?
Mhm.
And then I would want to see a drawing with just the geometry of the arch from one direction. And then that would lead, obviously, to then your max stand calcs and other calcs like that. So for the purposes of drawing, and just go through the exercise of perhaps taking this same view, but redoing it or overlaying it, but where you're just showing the wireframe
Okay.
of like the critical parts.
Yeah.
And that's the only exercise I can imagine.
Okay.
How did you actually draw this?
Oh, I found this picture. Yeah.
Very easy. And you should absolutely do that when you have SketchUp. So you just print a version for yourself and you trace it. It's
Yeah.
like, oh, I drew that out of nowhere. Yeah. Cool.
Can we just do that on SketchUp?
Yeah.
We can't like draw.
Oh, absolutely.
Okay, and then also for the spreadsheet one, I think I finished it, except for, I mean, I just have to look at the formulas for this, but is this all we're supposed to do? Like, the only thing is I couldn't figure out how to make these like jump incrementally like decimal point basis.
Oh, so right click on this on the bar.
Yeah, but it only allows for one. Like I put in my point one, and then when I say okay, it like if you look at it here, it just automatically changes to 0. And like the only option is like increments in units of one.
Super hot, super cute.
I'm not really sure how to change.
Jiggling all the time.
What if you made your formula something like that divided by 2?
Yeah.
I don't know what that looks like, but I'm sure that's how you do it.
But then you're gonna have to do real, like you're gonna have massive.
Or just hide this, and then your real D value is just that divided by 10.
Yeah, so
And then your
this divided by
slider
10.
increment is like 2 at the end.
Yeah, then you're gonna just have to like make this huge, right?
Yeah.
I mean, I guess.
Yeah, so you still need the number to show up as a full integer, and just hide that cell underneath your slider, and then the real cell, which you'll grab your D from, is cell divided by 10. And then consider that was a problem.
Okay. And then so all we're supposed to do is like do that there, and then solve for these formulas, and then is this all we have to do for the W shape?
Yep.
Okay, cool. Yeah, I did this and I didn't really know what I was supposed to be doing it.
That's fine.
Okay.
Cool.
I can't come on Tuesdays this week, but I was following the class like without sound.
Yeah. Sorry.
That's all right. But